Let's start it again. So first of all, the exercises lagged one line, which should have been there commented out for the Poisson distribution. That's the Poisson distribution random generation. Well, you could have rewritten it together with the mu, but it's here now. So that's what produces the plot here. And this is what I mentioned, that Poisson distributions with a high mean, large mean, they are quite close to normal distribution. There is some discrepancy, but you see the quality of the distribution. This is why we use for normal distribution also for fluxes, high fluxes. So that's for the last session. And so now I will start with how to quantify your ideas about distributions. First, the most naive estimator that you can imagine, and what that was very much used in statistics in the past, where you did not have computers, is the method of moments. It's just consists of trying to guess out the distribution. Here I plotted a Gaussian distribution, and we know from theory. You saw the tables in my list of distributions. They have some relationship between their mean and variance. Their theoretical mean and variance are defined by their parameters. This is very simple for the normal distribution, but can have different relation for different distributions, and even more of them if you have more parameters than 2 than 3 equations you should use. So you include skewness, for example. That also can be found on a sample. So here is a sample. Here is a theoretical distribution. We want to estimate its sigma and its mean. So we assume a distribution and equate the moments with of the distribution with the empirical moments. That's the simple principle. Here is another sample. The first question: can we assume a normal distribution, or what distribution we should assume? And if we can assume a normal distribution, then we can go ahead with simply equating these values to their empirical values. We see that the quantile plot is practically line-like. We are safe. We compute the empirical mean, the average, and the empirical variance, and these are the values that we obtain. The truth was quite close. It's all right. By the central limit theorem, you can give also confidence intervals for this, which I did not really do well. I did not compute here, and you could see that the truth is well within these confidence intervals. But estimation can be considered as good. Now, please turn again to the exercises. I hope there will be no more problems with them. Exercise 4, and please perform the first part of it, 4.1. If you do that, so for that you should read the data file that I gave, and then just make the plot. And you should see something similar like this. What you see is 2 outliers, or 3 even. Here, the cubic plot shows them very nicely, and the cubic plot shows also that these empirical estimators are not very good. So this line is defined by the intersect, as the intersect taken as the equating the intersect to the empirical mean, and the slope is given by the empirical standard deviation, and this is what you get. So obviously it's not good. Now, for outliers, this empirical moment method is not very good. So what you can apply? The truth was here, of course, a mixture, a normal mixture, with a high probability. P-mean is quite large. Here, I generated observations from this normal distribution, the same normal distribution as before, and but with a low probability, I added some observations from another distribution, and this is what produced the outliers. So in this case, you have, what can you do? So this is something that we observed with Gaia data when we simply wanted to assess whether a star, the time space of a star is a variable or not. We did have lots of outliers, and everything seemed to be variable because there was extra structure in the data. You see that the line is much line slope is very much deviating from what you should have. In this case, we did just a naive solution. We removed the outliers by some ad hoc way. It's not a very intelligent way to do that. Nevertheless, it's simple, so sometimes it will work. First, you define some limit over which you would like to clip with respect to the standard deviation of the sample, with respect to which you would like to remove observations that are too far away, and remove that. Repeat the whole thing again, starting with finding the standard deviation of the standard error of the data, the empirical standard deviation of the data. Again, you identify the outliers, remove them. So the problem is that with that, if a good idea about the phenomenon that produces this data is very interesting, then you might throw away valuable information. These observations might nevertheless be important to have a full idea about the process that you want to examine. So for that case, nevertheless, if you need the slope and the intersect for this line, what you can also do, use quantile estimators. So here, what I did is just to plot a line where the slope was defined by the median absolute deviation of the data. So this is something that you compute by subtracting from each data point the median of the whole data set, and take the absolute value of this. For the whole data, the median absolute deviation is taking these absolute deviations from the median and take the median of them. So that's the med here, up here. And this rescaling factor is adjusting the estimator to be equal to a normal distribution if you really do have a normal distribution in the background. So that constant factor makes a consistent estimator of the sample deviation, of the population deviation of it. So that's a more intelligent method to do that, to gain information on this part of your data. Another possibility is the IQR. IQR is just the difference between the 0.75 quantile and the 0.25 quantile. So the third quartile of the data minus the first quartile of the data. And again, there is a normalization factor that makes it a consistent estimator for the standard deviation of a really normal sample. Of course, all these estimators have a larger variance when you want to apply them to a true normal distribution without outliers. In that case, you are better off with the mean and the empirical variance. But at once, when you have outliers or any other discrepancies, you find that these are more stable, more robust.
And you don't lose all that much. The median's 2 over pi, root 2 over pi worse than the mean.
Yes.
So it's not an enormous kill.
No, but there are, yes. I think it's worse for the variance. If you observe the variance is worse. Yeah.
And so, Maria, if the distribution is not normal, though, how do these estimators work? How do they compare?
Well, you have I think you have to find the values how in the theoretical distribution the quantiles are related to the parameters of the distribution. Might not be very trivial. So this is for normal distribution, and I plotted it here because that's the most usual with which you want to work. But indeed, if you have a gamma distribution, if you have anything else, then these quantities, the IQR, you can go back to the cumulative probability distribution function of your distribution, of the gamma, of whatever else exponential. You compute you find the quantiles, this value, for example. This is relatively easy. It will be somehow expressed using the parameters of the distribution, and then you can compute back. It's not very, it's tedious, but can be done for many distributions, or solve numerically the resulting equations. It can be also done. But it's not very popular anymore in the statistical community. You have quantile regression. You have many applications. You can find procedures to do.
So why are you recommending, say, the interquartile mean rather than MAD estimator or something like
I
that?
don't want to recommend any of them. You can try it out and find out for yourself which is working better. Sorry, I don't have it. It should. Sorry.
And so how should we think about which of these robust estimators to use? I mean, there are lots of things, and you're the expert. And the idea.
Yeah, the problem is that I'm not that expert, and I don't have direct experience with them. So I would appreciate if you have experience with that.
I always use interquartile because I've always used it because I know the number is 0.741.
For example, you can go to the literature and see even on Wikipedia, probably it's there. What is the breakdown point of these estimators?
So I think the real question is what you're trying to do. I mean, the reason, this is answering your question, Adam. Yeah. You've got a distribution. You think it's basically Gaussian because it's got a noise in it. You want to know how broad it is. If you calculate the variance, you get garbage because the wings totally dominate it. So you say, I didn't like that. So you say, I still think that it's pretty much Gaussian. So then you say, in that case, I'll use one of these robust estimators. But that's not a very principled statement, which is why I don't think there's any very good answer to this. And you asked the question, what do you do if it's not Gaussian? Yeah. Well, what do you think it is? I mean, if you read papers by real statisticians or Hogg or somebody who's pretending to be, they'll tell you you should never clip things. I mean, this is basically a clipping approach. You should really be modeling the wings explicitly. I don't know if you're going to get onto that.
Are you saying then that we should be fitting like 2 Gaussians to a curve if it has those wings? Like
if you know enough about the wings, then you should fit a Gaussian plus something that's very, very wingy.
Well, that's what I'm saying. You do like a very flat Gaussian.
Yeah, but it's not clear it should be a Gaussian or a Cauchy or a T or something.
Okay.
So T's are nice because they smoothly go from Cauchy, which has no moments, not even a mean, the damn thing, all the way out to Gaussians that behave really nicely. But I don't think there's a good answer. But if you've got a distribution which is, say, a noise distribution from photon statistics, it's very close to Gaussian. It's not quite Gaussian. It's Poisson, you can do an Anscombe transform. But you've then got cosmic rays. So you say, well, I really, really don't care about those. In which case, anything that's estimating from the center of the distribution will get you what you want. So I don't think it matters very much. But that's why I was asking a real statistician. I mean, there are subtleties. I say the error in the median is root 2 over pi times the error in the mean. and you can calculate the corresponding errors for all the other estimators. So you could come up with a slightly better estimator, but whether it really matters, I care about errors in means, I care less about errors in variances typically, because they're so much more sensitive. They really depend on the fourth moment of the distribution.
Well, just two comments on that. Yeah. So first of all, you have to decide what exactly you want to estimate. If your distribution is not Gaussian, what is that? What is the parameter that is meaningful for you? It's not necessarily the distribution. It might be the location of it. It might be the mode of it. It might be the mean of it. It might be a lot of other things that. So you have to decide first this, and this might influence which method you want to do. The second, yes, there are, for example, to model data with outliers. For example, in classification, they use sometimes T distribution, multivariate T distributions instead of Gaussians. It's harder to do, takes longer, less stable, and so on. So that's sort of a choice. Sometimes you don't have choice, and you have to do that. You have, I think, there you impose. You don't estimate the tail index of the T distribution. You have to decide it. So again, you have to make some ad hoc decision, which is the best for your data. I just skimmed some papers on it just to get an idea of how it works. I don't know exactly how it's done, and are you able to really estimate how heavy should be the tail, and could the tail be different with different attributes? Normally it's multivariate, you have many attributes when you want to classify, and then whether you are able to choose. Maybe Adam will tell something about it. I don't know if you wanted to do that in classification, but it would be interesting for me too. Yes. Yeah.
Would you mind sharing those papers that you skimmed, just so that we have them?
Yeah, maybe I will just send them and put that in GitHub.
There's nothing principled about a T. I mean, a T is a ratio of an empirical to mean to empirical standard deviation. So that only in that limit is it a sensible
heuristic.
thing. Otherwise, it's a pure heuristic. Just because a student has his name on it doesn't mean you should use it. Who's a brilliant?
Yes. So whenever the other thing that I wanted to mention, outliers are outliers, so they are rare. Sometimes you don't have enough points of them to fit a more intricate model. You have to stick to simple models just because they tend to be more efficient in the center of the distribution. So if so actually what happened here, I took 3 contaminating distributions, so it was not one distribution, but this is itself a mixture. So if you want to get the right model in this case, you simply don't have enough observations, and that might be the case for a real life data where outliers can be produced by many different processes, and each of them follows different distributions. So maybe modeling them, it's not always a very good idea. You have to know what is interesting for you, and how to define the baseline for it, to what you want to measure your new effect, your interesting thing. That's a crucial question, how you define the zero model. Okay, so that's for robustness. Yes, so there exist general quantile estimators in many types of statistical things, statistical tasks. Wikipedia also has an entry on it, and as a starting point, trying to discover the quantile estimators, quantile regression, and so on. You can go there and find the not direct. It's a relatively good summary. I find Wikipedia quite useful for statistics. It's not bad for the first information, and often you find the basic references at the end. So go to the basic references and see what they say. And we have a third alternative for giving a robust estimate in these cases. You assume a distribution again, and define loss functions on it. Again, pure heuristics. So you don't know what works in your case. You have to guess it out. With robustness, that's often the case. So you put a loss function, like for example, simple least squares when you don't want to be very you trust your data that it has no contamination. That's the U squared, so that the residuals squared, or in the case when you want to estimate the mean by the sample mean, again this is the squared residual loss. You minimize this loss, and then you can arrive at your estimation. So this is Estimators, and they are very popular. They took the place, I think. So they are now more popular than quantile estimation. On the other hand, there are loss functions that give quantile estimators for you, so that they can be put under the head of Estimators. So here I show some examples of loss functions. Again, sorry about it, I cannot speak about them with my own experience. I did not try to compare them in my own work life. So this is the squared error loss that's usually used in linear regression in simple Gaussian likelihoods. You have absolute error loss when you minimize the absolute value of the residuals. You can have the Huber loss function, which has a parameter. Below this parameter, if observations are closer to zero, residuals are closer to zero than this parameter, then you have a squared error loss here, and then it levels out, and it will be similar to the absolute error loss. And then you have other things like Tukey's by-weight, which gives a constant loss for observations that are too far away. Again, very subjective, and if you are interested in it, you have to go to the statistical literature to check it out, how you can define these parameters. It's not equal. How important is to keep information at least partly in the details. If it's important, then maybe Huber's loss function is better for you because it penalizes less the faraway observations. Tukey's by-weight can be good if you want to completely cut off the effect of the very distant observations. Every very distant observations will have just a constant contribution.
So you can make a probabilistic interpretation of some of these. I mean, the first one, the sum of squared, assumes that the error of the distribution are Gaussian.
Yes. And
the sum of absolute residuals assumes that the error distribution is an exponential, double exponential,
yes.
I think.
Yes.
So what is the corresponding statistical model for either Huber or Tukey? Now, what I'm saying is that these are the things you get if you assume that the error distribution has particular forms. So we like squared because we believe things are Gaussian. But as Maria's just told you, they're not Gaussian, so then you try something else. But you can be more principled than just to say, I give up.
This corresponds, I think, to the least absolute deviation regression.
Yeah.
You can do something like, you can also do something similar. I wanted to mention it after the likelihood methods, that you put penalization on the parameters of the things on the residuals, and this penalization can also take the absolute value, which will lead to Lasso regression. But this is differencing. So here, absolute residuals, that is a L1 optimization, I think.
But doesn't that correspond to a double exponential? I think that's what you get for a maximum likelihood estimation for double exponential.
Yeah.
Yeah. So we're saying that these are all making some statements that are model for the residuals about the error distribution. don't they? So I mean that's the way
No,
you're
it's not
really
necessarily so. So again, I speak just by skimming the information in the literature, and it seems that these losses, even if this loss can correspond to an absolute to a double exponential likelihood, all the others are not necessarily so.
Well, that's
so
what
there is no likelihood model behind everything. So you cannot reason that my distribution is like this, and therefore I would like to use. Maximum likelihood can give you these things automatically if you recognize well your distribution with some diagnostic methods and with some intelligent data inspection, and then you can get something like this. But it's not necessarily so.
Okay,
so these loss functions are really subjective. They are introduced in a subjective way. Experts, knowing their domain, look at the data and say that this is not realistic. In this case, the data comes from a patient with cancer. It is not a realistic measurement. It must be bad. This is a bad measurement. They cut out.
So
or
in
they
astronomy, maybe that's less relevant. I mean, where we often do have a model. I mean, so that's why I don't know the answer. If there is a, I mean, apparently there isn't. But the bottom ones are really totally heuristic. We're usually better off than that. I mean, we have some model of what our data looks like, so you can come up with some reasonable way of dealing with it.
If you have enough data, yes.
Yeah.
But if you don't have enough data, then maybe it's better to stick to what you can estimate, and that's in the middle of the data, where you have more information. In the tails, when well, for Gaia, we considered these models too when we wanted to get a stable estimation whether an object is variable or not. So we had the photometric values of the star, and sometimes out of 20 you had 2 outliers. Okay, so what can we do? You cannot put a reasonable model on that. Of course, you could if you collect a lot of stars and make the assumption that all the outliers follow some similar. They come from some similar process that is dependence on the for example on the absolute magnitude, on the apparent magnitude of the star, on instrument state, on pointing or whatever. So this model for the outliers can be very involved, I think, and you have to consider if you have a reasonable chance to model these things. If not, then maybe these absolutely ad hoc models are better. That's what I can say. Okay, so I think this will be the next exercise, 4.2, if I am right. Yes, it is. So just please create the model, and I think you should see something like this. Here, what you see is some undulating thing around the line. It's practically line-like, but it has some differences from it, some systematic-looking differences from it. It's not that bad. We could accept that it's a normal distribution, but let's look at it more closely. You discover that there is a column called magnitude error for this star, and so in fact this is a heteroscedastic sample, an example of it. So again, I cannot say that the quantile what looks exactly in every case like this, but nevertheless you will see some discrepancies from the line, probably, if the sigmas are really far from being equal. What you can do is you can use the normality of the distribution, linearity of the normal distribution, and after finding the mean of the sample, you can just standardize these observations. So that's what I propose to do in the paper, and what you get should be something like this. Myself, I think.
So Maria, sorry, that plot you're showing right now, that's the quantile regression, correct?
Sorry?
The plot that you were just showing,
Yes,
that's for quantile regression?
This is the line is defined by the quantiles. If you want to get, I think this is the that's what I showed before. So this is now not the quantile line, but the usual line. So this is what you see without standardizing the data. If you standardize the data, then what should be? That's the result. The differences probably come from the difference of R's way to do that and Python's way of doing that. But actually, so it seems that it's a better fit. So it's more line-like, even if you see some discrepancy between the intersect and the slope of it. It's not that bad. So in this case, well, that's what you can use afterwards. Of course, you can use the given data. So again, for the next data set, please go to the slides again. So use the MAC5 in place of one outlier and find the standardization of these data. Plot it. What you get is practically horrible. So don't forget that you standardized it. It should be line-like with a practically slope of 1 if standardized, but it's not. So either the errors are badly given in this case, or so standardization. This is why standardization was wrong, or there is something else. And in such a case, it's just you go to your data and plot it as best as you can. You try to find indications of this bias. The thing that helps in my data set, in my simulated data set, is that you plot it against another information that is given in the data frame. It's not stable. So with time, there's a time coordinate given for it. If you plot it against time, then you see that it is changing. This was also an effect that we really observed with Gaia. I hope that this will not be the case with LSST because this effect came in the Gaia case from the contamination on the mirror. There was something losing water in the space, and it set on the mirror, and the mirrors were and as it accumulated over time, the mirrors get lost sensitivity. So it's so this was the reason to observe something like this. Then they decontaminated the mirror, they heated up the whole satellite, and the layer of water vapor went away from the mirrors. Then it became again good. So then that we would have observed again a drop in the magnitudes, and then yes, so it's magnitude. Sorry, it's not the astronomical way of doing it, but you could have observed also sharp drops in sharp brightening in the stars after the decontamination campaigns. So
Maria, we have a question.
yes.
So is this method of standardization, is it different for other distributions with heteroscedastic?
Yes. So what you have to know is that is it what is called in statistics location scale model. So if that's so, then the form of the shape of the distribution is similar if you apply such a linear transformation, a standardization of the distribution. There are others for which this is not exactly true, but usually if you go to even to Wikipedia, but to look at the distribution in some basic statistical textbook, I think there are many of them. Stewart and Kendall may give a lot of details on these distributions, and then you will find the information whether you can apply such a standardization on it. Okay, so that's it. So in these cases, what I wanted to show that you can have problems that cannot be treated with the method of movements. In this case, the method of movements is too naive and will fail, and then yes, so that's it. Here are the results. So we go to the likelihood methods, because also in these cases you can have some information about what model you should use, and if you have some model, some probabilistic model, and you have your physical model for what you are looking for, then you can apply likelihood methods. But yeah, so it depends on a good identification of the model. So what is the principle of maximum likelihood? First, you assume a distribution for the sample, and in this case, really bringing a quality change from the method of moments, you can assume a joint distribution for the sample. So you can you can account for also for correlations between data points, between, for example, in a linear regression, if the noise are correlated. For example, in Kepler, detection of planets was boosted by the application of Gaussian process models, where you can indeed introduce joint models for consecutive samples, because the errors with the Kepler with the dense Kepler data were correlated in time. Okay, so in principle, so here you have your probabilistic model for the whole sample, and you would according to the likelihood principle, you want to find the parameters that maximize the probability to obtain the observed sample. So that's the crucial thing. You take the logarithm of the likelihood because it's easier to deal with usually. Log likelihood is the probability density of the sample. We take the observed values as fixed values. They are not variable anymore. We observe them, they are put down on the table, and we don't change them. And we regard the parameters as its arguments. So that's the difference between the likelihood function and with the probability density function. Probability density function is a function of with fixed parameters, maybe unknown but fixed parameters, and but varying with the value of observation with the sample space. the log likelihood is a function of the parameters, and the sample is fixed. So that's the difference. On what quantity they depend. Okay, so that's the likelihood, and the estimating equations is you have to maximize the log likelihood with some method that is appropriate. Okay. Maximum likelihood estimators have some beautiful characteristics. For example, it is asymptotically normally distributed its estimate, and the way to estimate it, the variance covariance matrix of its parameters is particularly well, at least in theory, simple. Sometimes you have likelihoods for which this is not so simple as it looks like here. So, and you have to have some smoothness conditions on the likelihood, and also other conditions that ensure that for example, the parameter does not define the limit of the. So the parameter does not define the limit of the likelihood function. So it's you cannot estimate with this. For example, the uniform to estimate the maximum likelihood the parameter of the uniform distribution, the upper limit of the interval in which you can observe, you can have observations. This is not regular. So in that case, this is not true. So when the parameter defines the limit of the sample space, this does not work. On the other hand, otherwise, it is consistent, asymptotically at least, asymptotically unbiased. So the expected value of the estimated parameter is equal to the true parameter, and the sample size tends to infinity. As well, the variance of these estimated parameters is defined by the second derivative matrix of the log likelihood. It's not an easy thing to compute in each case. So you take the second derivative matrix of the log likelihood, and then take the expected value under two distribution. This is what is called the Fisher information, and then you have to invert it, and this will be the variance covariance matrix of the parameters. Now this is a bit unpractical because of course you don't know the true parameter value, but you can. Statisticians prove that you can take it at the. You can replace this estimator by the sample average at the estimated parameter value. So it's much easier. You can do that. This is the observed information. This is called the observed information. The Fisher information is the expected information. And then you can estimate the variance covariance matrix by taking the inverse of this sample average. This thing. Standard deviation of the maximum likelihood estimator of one component of the parameter vector is just taking the diagonal elements of this inverse matrix and take the square root of it, and you can base confidence intervals for theta. You have the quantiles of the normal distribution here. So if you want to a 95% confidence interval, then you can take this would be equal to 1.96. So that's for the nice properties of the maximum likelihood estimator. All this is not necessary. This is asymptotic, so it's not necessarily perfectly true to the finite sample. You will see. I will show an example of it. Okay, then another very nice property, and Robert warned me that I forgot to add a slide on this.
I just asked you if you were going to.
Yes, and that was very good because I indeed did forget it. So yes, so if The Cramer-Rao bound is defined quite generally for any estimator, actually any unbiased estimator. Let's call it T. Then the Cramer-Rao bound says that the covariance matrix of the estimator of this parameter vector cannot be better than the inverse of the information matrix. So variances and covariances between parameter elements are bounded from below by the observation, by the information, inverse of the information matrix. So if an estimator attains this limit, it is said to be efficient. Now the maximum likelihood is asymptotically unbiased, and therefore it is asymptotically also efficient when the sample size is large.
So this is a totally amazing result. It says that you can't do better than a certain amount. So you probably all know the result that the error in the mean is sigma squared over root n, sigma squared over n. That attains the maximum, that attains the MVB, the minimum variance bound. So that says you can't do better than that. The mean is the best possible way to estimate the properties of things. That's not in the least obvious. Nobody ever told you that.
In the case of non-misspecified model.
Sorry?
When you specify your model well.
No, it's the measure. It's the MVB.
Oh well.
The Cramer-Rao bound. You can't beat that. So that
you can be better if you consider biased
yes,
estimators.
the best unbiased estimator. So that's pretty amazing. I mean, you've taken Bayes' theorem. You've said we can estimate the probability of the observations given the data. So then you say, but I can't do that. So you say, I want the data given the observations, and that's the maximum likelihood estimator. And suddenly you've proved that asymptotically you can't do better than that. So you've got a constructive way in the limit of large samples of getting the best possible statistical estimator. That's pretty magic. I mean, you're never in that limit, and I'm sure that's what Maria's going to come to next. In small samples, all this stuff falls apart. But in the large sample limit, you've now got a constructive way of going from a model to an unbeatable estimator. That's good. You should be excited about that.
And
you should jump up and cheer.
Yeah,
very good. Louder, louder.
And this fantastic estimator in the large sample limit is equivalent to Bayesian estimators too. So that's
rah rah. Yeah. Go statistics.
Okay. So I did not want to go into such details as Robert said, but I wanted to go to examples. First example is estimation in our heteroscedastic sample. The log likelihood is, I hope again it's without typos. So you just take the logarithm of the density function I gave several slides before, and here you see the logarithm of the sigma I and the tan of the exponent, and there is a constant which is absolutely irrelevant with respect to where is the mean. So the mean can be here and there. If you add the constant, it's equal. So we don't care about this constant. It should be constant. Okay. What makes it nice that in this case we know the sigma. We trust our sigmas. It's not always true in astronomy that you can trust the error bars that are given, but in principle you can. And all that you must estimate is the mean. You just differentiate the likelihood with respect to the parameter of interest, that with respect to the mean. Theta, the vector of theta simply consists of the mean now. The derivative should be equated with 0 and solve the equation. In this case, that's an analytical solution. Here it is, the weighted sample mean. That's very simple. If you want to plot the likelihood here, yes, so we go to the time-dependent sample. It's a little bit more interesting. So it looked very, very nicely linear. So we put a linear model to the sample, and we want to estimate the intersect and the slope of this model. We write the likelihood again. Now I did not even write out the log sigma term because it's constant. We know the sigma again, and here it is what you have to see. Just for information, I plotted this log likelihood here, and you see that in this case the asymptotics are exact. So if you have a truly normal distribution, then the log likelihood surface will define as a function of the parameters something that is Gaussian. So this is equivalent to the statement that in this case the asymptotics are exact. So you don't. It's not asymptotic. It's valid for every number of observations. In this case, again, we can give a closed form solution to that. This is equivalent to the linear regression model. These are the formula, and here are the mean of the times and the mean of the axes. Again, the magnitudes and the weights are given here. So again, this looks very simple. And yes, so what I said, in this case, we normally distributed errors. That theory is completely exact. This is a surface of a normal distribution, a multivariate normal distribution. Okay. If we want to step ahead a little bit and try to put some more intricate model, like a linear model, a general linear model, a multivariate linear model here, and we relaxed the assumption of completely knowing the variance covariance matrix of the observations, then we still get a tractable likelihood. This is a very nice tractable likelihood, and again, if you maximize it just by mathematical way, differentiating it with respect to the parameter vector, that's what you get. So this is what you find for your solution. Now, depending on what you know about this sigma, the variance covariance matrix of this estimator, there can be many cases. Usually, when you do a multivariate linear regression, in statistics, in other real-life problems, not in astronomy, where you care to give errors on the observations, sometimes this is not known. You have to estimate it, and this is the most common case outside astronomy. You estimate it. This is the ordinary least squares. Sometimes you have this diagonal, and you know the observation. This is my previous example. Let's goes back again. You don't have to do anything about this estimation of sigma. When the matrix is unknown, again you have to estimate it, both in the case of general sigma and when it's diagonal. If you don't constrain it, then it's far too big to be estimated. If you with the n observations, it's a tough problem. So it must be constrained in some way, and one way to do that, to put some parametric structure on it, and that's what Gaussian processes do. And I think Robert will say something about it because he asked it. If I will say something about Gaussian likelihoods. So that's what I had to say. But we don't have to stop to use Gaussian models. We can use also, for example, the T-distribution as it was proposed. It was just by luck, but then you see. So here it is. Here is the density function again for a T-distribution. The log likelihood looks uglier than before. Numerical optimization is necessary to get a result. So again, you can find the second derivative by some numerical methods of this log likelihood, or even you have, if you feel okay with that, then you just take the pencil and a piece of paper and compute it, and put a negative sign in it and invert it, and that's it. That will be the variance of it. Let's see what it gives for a simulated sample. So I simulated 130 key 4 variates, so I knew the result. The estimation, the log likelihood failure that I get, the log likelihood surface that I got is like this. This is what I got. And the estimator, maximum likelihood estimator, gives the black line here. The truth is the orange line. So you see that it's pretty good. The confidence intervals, and in this case I plotted the 95% confidence intervals for that, as statisticians normally do. So they don't give the error bars, but the confidence intervals are 95%. That's what you see, and you see that this is somehow suspicious because the log likelihood is smaller on this side and in that side. In this case, it appears that the maximum likelihood method, the asymptotics, is not very good. Although it gives a very nice estimate, you cannot trust the confidence intervals. It's simply not close to Gaussian. It's not symmetric, simply. That's all. What happens when you simulate a sample of 13,000 P4 variables? It gets much better. We are closer to the asymptotic limit. You see the log likelihood surface plotted here. It's much closer to a quadratic one, so it's much. So the Gaussian distribution is a much better estimate of it. I plotted also the confidence intervals on it. The estimation is again very close to the one. So that's the effect. That's the asymptotic effect of it. And even though it's asymmetric, still asymmetric, it's closer to symmetric than with the 130 rates. So what I did now, I repeated now both simulations 5,000 times, repeated estimation also, and from all results, all estimated coefficients, I just took the quantiles given here. These give a symmetric 95% confidence interval, and what you can see, and this is what is plotted in this dotted line here. Dotted line here. So the confidence interval when I used the 130 observations was very far from the theoretically estimated confidence intervals. But on the other hand, when I repeated it with this high number of using this high number of observations, they were very close. You cannot even distinguish. They are so close. Maybe you can see at the ends of the points. They are. If I change between the slides, you might see the difference between if you focus on the dashed line. So they are from the simulation, the confidence bands from the simulations and from the theory. It's okay at this level. At this level, but that's very rare that you have this many data points. Now, again, these are subjective numbers, and they pertain only to this simulation, to the t variables. For another problem, that of course that will be different. But the general conclusion is that indeed the normal asymptotic normality of the maximum likelihood estimator is indeed asymptotic. Sometimes you have to use such Monte Carlo methods to assess what is indeed your range of plausible values. What could you have? To what extent you can be sure about your estimate? And Yeah, so again, just wanted to show again with the QQ plot version. I plotted here all the estimated values of degrees of freedom for the T distribution, and it's very non-normal. In the case of large samples, it is much better. Still not normal, but okay, it's close. Okay, so and also your likelihood can be sick. Sometimes you can specify. You can end up with likelihoods that are in some sort not well adapted to estimation. And this is the case when we had a scale shifted T-distributed sample from earlier. In that case, I just simulated the errors I took a constant mean and I simulated errors from a T4 distribution and scaled them up and added to the observation. So I shifted the mean, and also the T distribution is not the original T distribution, which is always standardized, but scaled with some model. You can see that this is the variance of a T variable as a function of the degrees of freedom. The minimal value is attained and in the infinity when the limiting distribution at mu equals infinity is the normal distribution. So that's the minimum that can be achieved, and all the others are bigger. And in our sample, the empirical variance was very low. So you see that it must be rescaled. So this is what is did here. I tried to insert instead of the original x, I tried to insert a standardized variable here. That's what you see here. The scale is a. So now we want to estimate both a and mu. Can we do that? So we take the likelihood and we plot it. And what we see is that with a, whatever slice you take, it is increasing. So it's bad. If you fix a somewhere, then you can optimize for mu. You can obtain a maximum likelihood estimate. There are cases where you are close to not seeing anything, but there still is an estimate for that. And the estimate is shifting. An estimate of mu is shifting with respect to a. It's somewhere here, close to mu equals very low values, very heavy tails. If you put a very low a, and then it just goes up somewhere like this. So this is a case of stick likelihood. If you take a look at the likelihood and try to find the differential of it, you get this formula of which you see a must be positive. That's just by definition. So this part is positive, this part is also positive because mu is also positive, this part is also positive. So this cannot be simply 0. Okay. All right. So that's what I wanted to say. Estimators maximum likelihood generalized on the distribution is non-Gaussian. You can estimate it. You can generalize it as you see non-Gaussian distributions. The model is non-linear. You can insert for the parameters for any model you want. You can extend to cases where you have to estimate the basis function also. That's smoothing generalized additive models. When in this case you have the basis functions as x, for example, or t, the time in the thing. It's just a linear function. So this is the basis function. Sometimes when you do a harmonic analysis, it's a harmonic function. It can be others. Also, so you see all sorts of extensions. what I wanted to speak about, and that's very quickly, classical hypothesis testing. So you have estimators now. You have to decide whether the data supports enough the presence of this new one of these new effects that is represented by a coefficient in your model. So the question goes back to the significance of this parameter. You have to specify the null hypothesis very well. So here, this is a time series of Kepler data with a suspected planet here. The zero hypothesis is that no planet here, only the star, and the alternative, there is a planet. So this needs to be put in a precise form. What is the null hypothesis? Is it white noise? Does it look like a white noise? No. Correlated white noise? Maybe. But maybe you have to insert also the modeling, something that models the granulation of the star, the magnetic cycles of the stars, and a lot of other things. I saw some papers on that, how to model the stars and put a model on that. So the null hypothesis should be made as precise as possible. And then you have a whole construction of hypothesis testing. Null hypothesis is called the H0. That's what you have to make as precise as possible. Then you select the test statistic and the significance level alpha. It's usually called alpha. The alternative hypothesis enters into the process by defining the test statistic. You define your test statistics in a way that corresponds to a double requirement. It is sensitive to the alternative hypothesis, so it's very distinctive, and also you know it's exactly its distribution for under H0. Okay, when you did that, you check model assumptions. Is it okay? Did I well specify the model, my model, independence of observations if you use that? Is it plausible? If you put some model on the correlation, is it plausible, and so on? Distributional assumption. Model assessment. Then you compute the observed value on the sample of the test statistic T. You compute the p-value of it because you know the distribution, and you can see how likely it is to obtain a more extreme value than your observed value. And you can make a decision according to the p-value. You cannot reject the model if the zero model, if the p-value is less than your significance level that you wish for. Significance level describes the proportion of error of bad rejections when the proportion of errors made by rejection of H0 when you repeat the experience many times, and if the p-value is smaller than the significance value, then you reject the zero hypothesis and you accept your alternative, which is a good thing. Nevertheless, it still has a probability p that it was the zero hypothesis that produced such an extreme value. So if you repeat your exercise on a different data set and again nothing, you have to take into account that just by any chance you can observe significant p-value if you try a lot. So that's not a good thing, but in the pharmaceutical industry, many cases you see that they make experiments, nothing to see, again nothing to see. They try to see something, and finally they end up with seeing something very significant, and they produce some paper. There is an effect, and often it turns out that this is just by chance. Okay, so this is just to mention the meaning of the test statistic, it does not mean that your alternative hypothesis that you wanted to support with your data is true. There might be caveats. For example, the test statistics meaning is just the assumed null model wasn't very likely to produce such an extreme observation, such an extreme test statistics. That's all. It does not mean anything else. There might be other effects that produce such an extreme value. You have to consider carefully what can produce something like this. Also, how likely was H0 originally, and then what was the prior probability of your effect? There are very unlikely effects. If you find it with a very high significance level, then you can be sure. But if that's just barely, it's still much more likely by this conditional arguments that it was still just by chance, because it was very unlikely in the first place. It can be, but you need more data to support it. And here, this is just definition of errors as it's usually given. You can find similar things in Wikipedia too. Okay, I don't think I will go into details with these things. Likelihood ratio test, again, you find literature about it. Classical tests, here is a list of them, and many more. These are harder to find, I found, but yeah, so that's something to. What I would like to speak about in 5 minutes is model selection. So this is again the formal sample of time-dependent longitudes. I put 3 different models on it. One is linear, one is quadratic, and one is a smooth spline. Which to choose? So model selection. Most frequently used methods, likelihood ratio. Now here, you can do it only for the first two. The linear model and the quadratic model are nested. So the linear model is obtained by just forgetting about the quadratic term. They are nested. The likelihood ratio test is quite permissive and does not take into account the fact that a larger model, the larger model is always an improvement on the data, simply because you introduce more degrees of freedom that can account for more variability, and you optimize the likelihood. So it will be anyway an improvement. To protect themselves against this effect, Akaike information criterion was invented. It gives a penalization for the number of the parameters in the model. Twice the number of parameters for which you optimize. And this one you can use also for non-nested models. For example, if you can use, for example, the smoother matrix, trace of the smoother matrix to find an approximate degrees of freedom to put in the place of 3 here, and you find the log likelihood. You can find it from the sum of squares. You can again compare models which are not nested, which are based on different principles, but you can find likelihood, you can find number of parameters, and you can also you also use the same data. So that's important. You have to use the same data, no change in the data. Otherwise, it becomes uncomparable. This is not consistent in the sense that if your sample size grows, it will select a larger model than the true. But nevertheless, it's more conservative than the likelihood ratio, so it leads to more parsimonious models. The one which is consistent if n goes to infinity and which selects the correct model in a large sample limit is the Bayesian information criterion. This is a stricter penalization because it not just penalizes with the number of coefficients, but also it depends on the number of observations. This is again also can be used also for non-nested models, and again, so more conservative. This is the most conservative, but for small samples it is too conservative. So simply data science experience says that if you have small data, then you are better off with the Akaike information criterion or some modified version of it. and well, many modified versions. And thank you. Unfortunately, there was no time for the exercise. I am very sorry for that, but it's there on the GitHub, and you are very welcome to do that and ask me questions about it. So it would be very nice to won't waste time on it.
All right, so are there any questions for Maria? I have a suspicion everyone's very hungry. So